A very warm welcome. This is Debduhita Banerjee, registration number 20 BCE 1429, and my topic for digital assignment 2 is building a Merkle tree. So, first getting started, let us ask a very basic question. What is a Merkle tree? So, to define a Merkle tree, we can say that a Merkle tree is also known as a hash tree. It is a data structure used for data verification and synchronization. It is a basic tree data structure where each non-leaf node is a hash of its child nodes. All the leaf nodes are at the same depth and are as far left as possible. A Merkle tree helps to maintain the data integrity using hash functions. So to know more about Merkle trees, we must first understand the basic of a hash function. To define a hash function, we can say it is a function which maps an input to an output of fixed length or a fixed number of bits. This particular output we call as hash. And this output is unique for every input, and this can enable fingerprinting of data. So huge amounts of data can be easily identified through their hash. Some examples of hash function are message digest function, secure hashing algorithm, etc. So coming back to the topic of Merkle tree, we can say that in cryptography and computer science, a hash tree or Merkle tree is a tree in which every leaf node is labeled with cryptographic hash of a data block. Every node that is not a leaf is labeled with cryptographic hash of the labels of its child or children nodes. A hash tree allows efficient and secure verification of the contents of a large data structure. A hash tree is a generalization of a hash list and a hash chain. Demonstrating that a leaf node is a part of a given binary hash tree requires computing a number of hashes proportional to the logarithm of the number of leaf nodes present in the tree. Conversely, we can say that in a hash list, the number is proportional to the number of leaf nodes itself. A Merkle tree can be thought as an efficient example of a cryptographic commitment scheme in which the root of the tree is seen as the commitment and the leaf nodes can be revealed and proven to be part of the original commitment. Thus, a Merkle tree stores all the transactions in a block by producing a digital fingerprint of the entire set of transactions. It allows the user to verify whether a transaction can be included in a block or not. Merkle trees are created by repeatedly calculating hashing pairs of nodes until there is only one left. This hash is called the Merkle root or root hash. Thus, the Merkle trees are constructed in a bottom-up approach. So, delving a little more deep into the Merkle tree structure, we can say that every node is a hash of transactional data in a blockchain, and the non-leaf node is a hash of the previous hashes. Merkle trees are a form of binary tree, so it definitely requires an even number of leaf nodes. If by chance there is an odd number of transactions, the last hash will be duplicated once to create an even number of hashes. So here we have an example of a simple form of a Merkle tree. That is a binary Merkle tree. Here we have 4 transactions in the block: TX1, transaction 1, transaction 2, transaction 3, and transaction 4. We can see there is a top hash, which is the hash of the entire tree, which is known as the Merkle root. Each of this is repeatedly hashed and stored in each leaf node, resulting in hash 0, 1, 2, and 3. Consecutive pairs of leaf nodes are then summarized in a parent node by hashing hash 0 and hash 1, and which results in hash 01, and separately hashing hash 2 and hash 3, which correspondingly results in hash 23. Then the following two hashes, hash 01 and hash 3, are then hashed again to produce the root node or the Merkle tree node. Merkle root is stored in the block header. The block header is the part of the Bitcoin block which gets hashed in the process of mining. It contains the hash of the last block, a nonce, and the root hash of all the transactions, as we can see in this diagram. So having the Merkle root in a block header makes the transaction tamper-proof. As this root hash includes the hashes of all the transactions within the block, these transactions may result in saving the disk space. If we change any single transaction, this will result in a chain reaction in which all the subsequent top-level hashes will be modified, including the Merkle tree root, and thus we can easily detect the tampering of data. So now let's get to real implementation and let's build a Merkle tree. So here we have an implementation, a simple implementation of the Merkle tree in Python. Here we have imported the hashlib library, which has been used to generate hashes for the nodes or the leaves. We have defined a class called node, and here we have the init function, which is basically to define each of the components and to initialize them. Like each node will have a left root, a right node, its value content. Then we have the hash function. Uh, we are using the hashlib library and to generate the SHA-256 algorithm and generate the hash function for each node. Um, the value of each node is passed as a string, which will be the message or the transaction contained in each node. So we also have a copy constructor here to initialize the node. We have a second class called the Merkle tree, and we also have the init function to initialize the build tree function. Here in the build tree, we are first checking if the number of leaf nodes are even or not. If the leaf node is odd, uh, we are appending the last node again to the tree so that overall we get even number of nodes. If we have the total number of nodes as 2, then we return node 0 and node 1, and we compute the combined hash of the value of node 1 concatenated with the value of node 2. Then we return the Merkle tree root hash. If it is not, the length is not 2, then we correspondingly go to the left node of the tree and then to the right node of the tree, and we concatenate the values as required. Finally, to print the tree, we do a tree traversal. We check if the left node is empty. If it is empty, we directly print the values, or else we traverse the right nodes and check the corresponding values. Here we have defined a Merkle tree with the following elements. These elements can be thought of as the messages or the transactions in a blockchain. Here I have defined 7 different messages like transaction 1, transaction 2, transaction 3, 4, 5, and 7. Here we have an odd number of transactions or elements. So um, the last node will be duplicated and added to the tree to generate the even number of nodes. Let's run this code and check the output. As we can see here, um, first the entire root hash is generated. which is the hash of the entire Merkle tree, containing all the transactions. We can check the content as it is the hash of transaction 1, 2, 3, 4, 5, 6, 7, and 7 has been duplicated 2 times so that it is a full binary tree with even number of nodes. And we can also check the hash of the left subtree of the root node and the hash of the right subtree of the root node. Um, Next, we have the left. When we traverse back to the left subtree of the root node, and we have a subsequent hash value of the left root and the right node, and this is the combined hash of transaction 1, 2, 3, and 4. Next, similarly, traversing the tree will have the uh, hashes of combined hash of transaction 1 and only transaction 2. And then we'll get the hash of transaction 1, transaction 2, and now we go into the right subtree and we get transaction 3, transaction 4, and individual hashes of transaction 3 and 4, and combined hashes of the next subtree, which has transaction 5, 6, and 7 duplicated 2 times, then subsequently transaction 5, transaction 6, and correspondingly we get uh, the hash of transaction 7 repeated 2 times. Now we can see how the data tampering can be detected in a Merkle tree. Let us change the value of any one of the node values. We can change the transaction 7 here to be hello, and we'll run the code again. So we can see at the last stage, hello has been duplicated twice because it is the last odd number of odd numbered node, and the corresponding hash value of the hello is very different from what the hash value that we had when it was transaction 7. And correspondingly, each level's hash has been changed, as we can see. And finally, we check the root hash. And even the root hash is completely different from the previous root hash that we checked. This is the root hash of the new tree with hello, with transaction 1, 2, 3, 4, 5, 6, and hello. And this is the root hash with 83390 with the original Merkle tree. So we can see that even changing one single transaction can change each level's hash and also the root hash, and thus we can easily detect tampering of data. So coming back to our presentation, so as we have seen, in a binary Merkle tree, we can now explore the complexities involved. Like for a binary Merkle tree, the space complexity is O of n. For searching a binary Merkle tree, the time complexity is O of log n. For tree traversal, the corresponding time complexity is O of n. For insertion and deletion, it is again O of log n, and also synchronization is O of log n. So here we have a brief idea about what is a binary Merkle tree and how we implement it. And that's all for this presentation. Thank you.